So, before we start to discuss the detail, I just want to re-emphasize the design decisions. We want a coarse-grained decoupled redundancy. What that means is we don't want this to be lockstepped. I think that's increasingly difficult to achieve. But also decoupled in the sense that we don't want the circuit to be tightly integrated on a critical path. We want it to be on the side. So in the common case where you don't worry about reliability of your program, this logic is not turned on, and it doesn't cost you. At least it doesn't cost you much. So that's one desire. The second desire is we don't want to use this commonly used notion, which is a wrong notion, that because there's non-determinism, if I execute two parallel codes, I may not get thread-to-thread comparability. That thread 1 in one execution is always producing the same result as thread 2, so that's a problem. And one way to suppress the problem is to make sure that one of the thread groups always passes on whatever value they read to the redundant group, and then the redundant group will not get a different outcome. And we don't want to do that. We want the two thread groups to completely independently execute the program. Now, that doesn't mean we're getting around the non-determinism problem. It's a problem. We have to suppress that. So here's the idea. It's a high-level model of how this thing goes. We would have a couple of threads. These are your regular thread, if you wish. We call them the computing thread. Let's, without loss of generality, assume we have n of those. What we wanted to do is to launch another n threads. This part is it's a cost that you're willing to bear. You're going to lose your throughput. Instead of executing possibly two n threads, now you're only going to execute n semantic threads. Okay, this part is understood. When you want redundancy, you're paying something. So what we want to do is to let them run for a while. How long? Thousands of instructions. So definitely not one cycle. And at some point, we take a checkpoint. We stop everyone. And in fact, we don't stop it as in block every stage of the pipeline. The only stage that needs to be blocked is the commit stage. So you've committed these instructions from T1, and now all future instructions can still propagate in the pipeline, executing, loading value, doing whatever they do, but they cannot commit. Then I can take an architectural snapshot, architectural state snapshot. I can read all the registers and see what the current state of the architectural state, the register state is. So that may take tens of cycles to copy all your architectural register, and it needs hundreds of bytes of high-speed buffer. So we assume that. So now later on, the same execution, the same thread group, but executed redundantly in a different set of processors, would be stopped at the same point. Okay, you will remember that. You will say, okay, there are let's say 1,000 instructions executed here, and now here, by the time you commit 1,000 instructions, you would stop it. You say, okay, I've reached the same checkpoint. Let me extract the architectural register state, and since I already have the checkpoint from the computing wavefront, and this whole group of thread that we call the verification wavefront, we'll just compare that checkpoint with this checkpoint. Okay? If they're the same, that means after these execution, after these many instructions, we reach the same architectural state as far as register is concerned, and good. this part seems to be error-free, and we can continue, right? And by some point, if we detected a difference, we say, okay, they don't agree, so one of them is wrong. Remember Charles Babbage farming out his computation to two sets. When they check out, when the results are the same, we don't know that the result is correct. We just know that the chance that is incorrect due to some random error is smaller than if we trust the result without checking it. And when we see that they're different, we know at least one of them is wrong. We don't know which one. If we have three or more, we can try to do a majority vote and assume the majority of the results are correct, and maybe correct the wrong one rather than abandoning the result. But here we don't assume that. We just assume detection is more than enough, because in most cases, if you're worried about a particle-induced error or these random hardware events, they're not very frequent. Okay? So we want to optimize for the common frequent case, not these rare cases. So if we detect an error, we know that it must have happened in this epoch. Okay? Because last time everything was fine. We started from the same point, we proceeded, and now we differ. So what we do is to kill the current execution, to say, forget it, you can squash, reload that checkpoint, reload the states, and continue from there. So of course the state includes a lot of other things, your PC for every thread, and we will see later also the memory state. We're only talking about register comparison here. So what about memory? And that will come up in a little bit. But in general, we have some state. We compare the two states. If this group of computation did not move the state to a consistent, to the same state, A did not move the state to the same form as B, then something is wrong, and we retry that by loading the checkpoint before this part of the computation. So that's what you do. It's a little too busy. You reload checkpoint and you re-execute from there, and hopefully problem goes away if it's a soft error, meaning it's a transient event, not a permanent error. If it's a permanent error, you might have to do some additional work. We'll ignore that for now. I mean, you can retry this, and if the second try you disagree again, then you can load some code from the operating system to try to detect any permanent error on the hardware. Okay, so obviously, if you're doing redundant execution, you have some problems. Here is the problem that I was talking about earlier, and it's a more concrete example, what I call non-determinism. So you see I have two instructions over here. One loads from a memory location, and let's assume this memory location, 0 offset of register R4, happens to be the same as that on another thread in the wavefront. Notice the difference in the execution order in the compute wavefront and the verification wavefront, assuming the vertical position somehow indicates the timing. Okay, so on the left hand side, the store happened later than the load, so the load would have loaded the earlier version, whereas in a new execution, this didn't happen for whatever reason. Branch misprediction on this thread, making instructions executing slower, whatever, this can happen. So you can see, if I run the same program where I have this situation, this is by the way called a race, okay, two memory operations, at least one of them is a store, and they have a race in terms of their execution sequence, and if they're executed in a different sequence, the program's outcome can be different. Now, this may be a bug, but we're assuming that this doesn't inherently mean it's a bug, but it could be a bug, and you may want to get rid of it. At least it's not a good thing to have, but nonetheless they exist. Races exist, so if you run the parallel program multiple times, they may have different outcomes. The result may still be useful for you. Imagine you have a program where your load balancing is this. Your work is cut out into a linked list of chunks, and whoever finishes a chunk comes in, grab another chunk and process it. Okay, so if you have a program like that, you execute it multiple times, they will always do all of the jobs, but perhaps in different order, and different parts are executed by different threads. So that's what I mean by non-determinism. When you execute it again, you cannot expect, the thread called T1 in the new run would always do exactly the same thing as that from the T1 in the previous run. But that's what we are relying on here to detect error. We're assuming the only reason these two threads would do anything different that lead out to different temporary intermediate state is due to some error. Okay, then non-determinism is a problem, because non-determinism leads to difference in state, but it's not a hardware error. So what do? Right? We have to worry about it. We have to suppress this kind of ordering. One thing you can think about is, suppose we remember the order that happened here and prevent this instruction from executing too early. We simply insert some pipeline bubbles, delay it. When it is delayed sufficiently, then it will execute the way we want it to execute. So this verification wavefront, the job is not to run any possible ordering and see if it agrees with the computing wavefront bit by bit at every time point. No, it's to check one execution sequence, it's to check that particular execution sequence and see if we got anything wrong. So we'll have to deal with this. This comes later. So, but in general, what do? We create checkpoints, we compare them, and the checkpoint has to include more than just register state. It also has to include memory state, right? Or the difference in memory state. So how do we propose to do that? Okay. Now, this checkpoint, the creation of it, the verification of it, obviously introduces overhead. We don't want to do this very often. If we do this every instruction, then the program is going to be too slow when we're executing in the redundant state. So that's another thing to keep in mind when we're designing this. But it turns out this is not difficult to do. We haven't been doing this in modern microprocessors, at least none of the commercial product I'm aware of did any of this proposal. But if you think about it, it's not difficult to do. And all we needed to do is to add some peripheral logic. And I drew this deliberately outside the core. It's really not on the timing critical path. Okay? And I call this the TLR logic, the thread level redundancy logic. You can turn it on when you want to use it, you can shut it off, and it wouldn't affect the rest of the pipeline. What does it have? It has the checkpoint buffer. That's basically the register content. And you may want to have many more than just one checkpoint running around for efficiency. So every epoch, you create a checkpoint that's your 64 architectural register, your PC, so if it's a separate register, so you have the content of all of that, and you have a buffer that keeps the stores that you executed in a particular epoch. We call that the post-commit buffer, or PCB, and I'll explain that. in the subsequent slide. So that's all you need. This is your stuff. And while you're executing, the processor really isn't aware of your logic. It just executes. It goes to L1, it reads, writes completely normally. But every now and then, you may have to be stopped, again, only at the commit stage, to engage in some logic that copies stuff. So this is really what it involves. And if an error gets detected, then you flush the pipeline, reload it, and that's exceedingly rare. So all that logic is peripheral to the main call. It's not very frequently used. Okay. And for store, we handle it slightly differently than you would otherwise assume. You can think of it in the sense that a store is a dangerous thing, okay? Because we haven't verified this piece of code. Let's go back. If we have a store over here, we cannot allow that to permanently modify the architectural state, okay? Because our checkpoint is not that big. If we have a checkpoint that copies the entire architectural state, including all your memory state, and we can reload it, fine. You can allow the memory to change the state because you can always restore it. But no, we don't copy all the memory content as the checkpoint. So for memory content, stores need to be buffered. So you need to put them aside to say, I need to make sure that everything is right before you're allowed to modify the memory, okay? Rather than if something is wrong, we somehow can restore the previous content. So all the writes have to be buffered into the post-commit buffer. So the core will retire them. Why? Because we want the epochs to be very long. We cannot hope the core to buffer all these stores in its tiny little store queue. So we'll put them in a much larger queue. You can think about this as just a secondary, large, gigantic store queue outside the processor. So that's the post-commit buffer. But to make sure we don't increase the timing critical path, we don't complicate the timing critical path. We don't change how stores are handled in the L1 cache. So stores are allowed to go to L1 cache. So L1 cache is not to be trusted. Okay, if we find we have an error, again, which is very rare, we'll roll back, we'll throw away everything in the L1 cache. Okay, so we can write to L1 cache. We can think about it as being speculative. So we write to this L1 cache. If a dirty line gets evicted, you cannot write back to the L2 cache. In our case, this is, we'll assume we have all this logic that is TLR related in shaded area, okay, and we have the private cache is just L1 cache, all right, and this whole thing is your core. You get to stamp out multiple copies of it, so there are 2N in a chip multiprocessor. This is logic relationship, by the way. You can have this as distributed shared memory machine. It all works. But the platform that we were assuming is a chip multiprocessor where you have these cores, and so the L2 is the shared cache. I mean, if your L2 is a private cache, so then just imagine there's another L2 over here, and dirty data or unverified data can be allowed to enter into both L1 and L2, but then they have to go through PCB to go to the last level cache, L3. Okay, so the number of levels of cache doesn't really matter here. Now, again, every epoch would stall the commit, checkpoint all the register, and all the stores have to be simultaneously accepted by the L1 cache as well as the PCB, and then verification of an epoch really just consists of comparing the PCB result from one thread to another. So thread 1 might have produced 4 stores in this epoch, and then it would be something like that with address and data, and this would be part of your checkpoint, and you will send this to the counterpart T1 prime and compare. So if everything matches, then you're fine. That means the final state of the registers are the same and the incremental change to memory is the same. That's why you can agree that the effect of this epoch, the T1 copy of it, is the same as T1 prime's copy. So that's what PCB does. Okay. Now, some of the writes, so all the writes are buffered in PCB. But if you have a dirty copy, a dirty data in L1, remember what you do? If it's evicted, you cannot write it back. Why? Because we don't know if it's correct. We don't know if it's verified. So now, if you have a data X, and the value is 4 because you've already written to it, so X is 4, it's in the cache line, and it's evicted because of replacement, because of cache conflict, so it's gone. Now obviously X equal 4 has been recorded in PCB, but this copy is gone, no longer there. So now I have an L1 miss. What do? I go to L2. L2 doesn't have X. L2's X is still old because we haven't validated the epoch yet, so it's being buffered. So you see, you cannot go to L2 directly when you have a miss. Okay, so every miss in L1 now needs to search the PCB. Okay, and this is what you have to worry about. Not a big deal, but if you think about it, essentially your store queue, one way to think about it is the store queue stores things uncommitted, but PCB stores things that's unverified. So just like you have to search SQ, the store queue, when you have a load, you have to search PCB when you have an L1 miss. Okay? So, if you remember, I talked about store queue being such a painful piece of logic to make it fast and everything and correct. What's happening to PCB? How big of a problem is it? Well, we're talking about thousands of cycles. In 1,000 cycles, you're executing on the orders of 1,000 instructions, and about 10-20% of them might be store. So you're talking about hundreds of stores. So if I was bemoaning about the difficulty to make a 32-entry store queue fit in the timing budget, how am I going to support PCB with one epoch already on the orders of hundreds of entries, and we may have more than one epoch keeping around? Isn't it just asking for a magic piece of hardware? No. I'll show you how this is optimized. It's not difficult at all. And the key insight is really we don't check PCB all that often. Okay? We're only checking it on a miss. And that's a crucial advantage that we have. Because of that, we can do a lot of optimization. Not just because of that it's not a problem, but because of that I can do optimizations. Okay, so this is how it works. Here I'm throwing away everything, the core, the register, the L2, the L1 caches. I'm only showing you the PCBs, okay? And I have multiple. I'm showing you 3, but I may have enough PCB entry to hold 8 epochs, depends on what I need. So the epochs are shown in here, right? Every epoch, I have many entries. Oh, by the way, if you design a fixed size entry, you say, okay, an epoch contains 32 entry or whatever entries of PCB then when you run out of PCB, then you have to terminate that epoch. You have to say, okay, that's the end of this epoch. Everybody take a checkpoint, and then we move on, so we can use the next set of buffers, the next epoch PCB. All right. So here, and another crucial thing is, even though every store that I commit should be somehow captured by PCB, my PCB is not organized by words or by stores. They're really organized by cache lines. So an entry in PCB is a cache line. Maybe it contains just one store to one word inside the entire cache line. Maybe it contains 7 stores to the entire cache line, but this is the unit that we decide to stay with. It's much more efficient that way to match the size of your cache. So all of these entries that you're seeing over here, they're all cache line size. Okay. So let's walk through some examples to show you some of the properties. Okay. So the PCB, again, the PCB is divided into sections, each section corresponding to an epoch. Every write has to go into the L1 as well as the PCB, and if it doesn't exist already in that section of the PCB, we allocate a new line, copy the entire line from L1 to PCB, and put the write in it. Okay, so I'm giving you an example. Over here, we're following a particular cache line that contains address X, and this is being accessed a couple of times. First by T1, then by T2, then by T3 in the same epoch, and lastly by one more store at T3 in a different epoch. Okay, so how many versions of this cache line will exist in PCB? Well, it's 4. As you can see over here, the 4 versions, V1 all the way to V4. And this is what happens. At the first epoch, the epoch 4, the first effort, you write, okay, we allocate an entry. The tag is X, this is cache line X, and right now it's valid. Okay, so if I miss in the cache, in my L1 cache, I have to come to my PCB and search. And if I try to read from X, I will have to get it from here. In fact, I will copy this line back into L1. So by the way, then you can kind of imagine this section is fully associative. So we just keep one after another. It's not organized by index or anything like that. So this is the first version. And then in the next epoch, I want to do a store. Now imagine, just think about this. PCB is essentially part of my cache. It's just a bigger cache, right? It's my L1 cache can evict some lines, but I have some rules about certain lines. I cannot evict them. I cannot write them back to the L2 cache. So really, PCB is part of your cache. So anything you know about cache coherence applies here. So if I want to invalidate a line, what I used to do is I go to that line, I go to that cache, I check to see if it has the line in its cache, and if it exists, I invalidate it. This whole thing has to be done as well. So when T2 issues the store, okay, it needs to first obtain the exclusive state and then invalidate T1's copy, right? And we have to do the same to PCB. There is only one exception, that we added a state. I call this the superseded state, okay, or superseded, or SD. So we changed the state in PCB from valid to superseded, SD. Why? Superseded simply means now this is no longer valid. Okay, no longer valid. So if I have an L1 miss, I check my PCB, I see the state to be in superseded state. What do? I cannot use that value. That value is not valid. So why not just get rid of it completely? Well, here is the thing. This instruction belongs to an epoch that we don't know if it will survive. This may be killed. Okay, so if this is killed because of an error with the rollback, then that value would be the last legal value. So this cache line in the PCB cannot be thrown away. It's a record. I have to keep it. And when this epoch is found out, the epoch 4 is found out to be correct, we have to update the next level cache with this value. So that it has to stay inside. Okay? All right. What if I have the copy, we have the version of X, and T2 was writing to it. Okay, so now it becomes valid state, right? This is what happens after this instruction. And in the same epoch, someone else does a write, this time T3. So T3 will have a copy of V. So you can see this time, this copy in T2 should be invalidated. Why? Because by the end of this epoch, if this epoch 5, has checked out fine, the PCB that's going to write the correct state of cache line X into the next level of the memory is going to be the PCB of T3. Is going to be this one. So our entire cache line is over here. So this is now the valid state. This is completely useless. Even if we roll back, we wouldn't need this. We would be rolling back either to this one or to this one at here. You get that? Okay. Finally, even if suppose after an epoch the same thread wrote to it again. Okay, so a new copy is made, V4. It's valid, and just like I have to invalidate everybody else, I also invalidate my own copy so that it becomes superseded. Again, if I have a miss, I search in my PCB, it is this newest value of X that should supply the result, not version 3 anymore. That's superseded. So the only reason for a superseded state to stay is occasionally or at the end of a validation of an epoch, we write the incremental update of state to L2. Okay, so there's a very interesting property out of this. At any point, one cache line can only have one valid copy in all the PCBs. Okay, you can have a lot of invalid copy. We never bother about them. You can have a couple of SDs superseded, one per epoch, but you can only have at most one cache line that's in valid state. This is a useful property that later will come to help us. So now we know how this works. If we go through this, coherence is fine, because when we need to do invalidation, we did it. And as far as coherence is concerned, if you have a miss from any cache line, you have to search all PCBs. Okay? Just like when you have a miss, you need to know who has the data. I'm assuming a bus-based system, so then we have to search all the PCBs like SNU. But if you have a coherence protocol, you have a coherence directory, and that works too. So in this case, this node would be in the directory. So anybody who has a miss from L1 will go and read the directory information. The directory would basically say, well, thread T3 has a copy of it. Okay, and by the way, this is completely independent for the compute wavefront and the verification wavefront. They each have their own coherence. A thread will from one wavefront will not read value from a different wavefront. Okay, so we have this. The PCB is part of the cache. So the correctness is kind of guaranteed because we sort of just extended what the cache is, and everything else is handled just like in the coherence. If there's a write, we have to invalidate. There's read, we intervene, we provide the value. It's just in the past, we only need to check the cache to see if you have a value that you need to invalidate, to see if you have a modified version that you need to use to intervene. Now, anything you have to do, you have to check your PCB, but still it's correct. Okay, now what happens when I have a miss? Well, when I have a miss, I have to check my PCB. I mean an L1 miss. When I have an external snoop, an external request, I have to check my PCB. If I have a write to any cache line, I have to update my PCB. So that's when I access my PCB. And my PCB is gigantic. It's associative, so I have to search for the address. I don't like that. That's going to be too expensive, too slow, too energy hungry. So here comes 2 optimizations, and after that, after both optimizations, it turns out you barely need to touch your PCB. Optimization 1. This time I do have to touch the cache. I'm gonna change the cache to add one more field. So I used to have tag, data, and state, which I didn't draw here. Now I need to increase that metadata by adding a pointer to point to one entry in the PCB. Okay? So remember, PCB is large only in the sense if it's an associative queue that I have to search 300 entries or maybe 1,000 entries. Any entry can be a match, and I have to potentially priority encode things. Oh, by the way, I forgot this part. We don't need priority encoding, unlike store queue. Why? And that's again because any copy, if you look at any PCB, there is only one valid entry. At most one valid entry. You can have a lot of superseded, but only one valid entry. So you don't need to priority encode this. You don't have to say, okay, there are 2 copies. Somehow I have to know this is newer than that, therefore I use this. No, this one is not even in valid state. So when you're searching your PCB, you don't need to find out to determine between multiple valid states. There is only one cache line that's going to be in valid state. Okay. So anyways, since this is still a fully associative queue, I don't want to search it. But accessing it is a completely different story. So if I have a pointer, every cache line that exists in the PCB will have a pointer to connect the cache line version to the PCB version. How does that help? Well, suppose I have a cache line Y, and I already wrote something to it, and I therefore created a copy of it in the current section in my PCB. Next time I write to a different word, I simply follow this and update that word. I don't have to search. So remember, I have to search my PCB when? Well, when these 3 conditions. 1, there's a miss. 2, there's a write. And 3, when there's a invalidation or other coherence check. I'll call that snoop for simplicity. Okay. Every time, in theory, if I don't have any optimization, I have to search. Okay. You want to write? Want to write memory location X? Let's do an associative search to see if X is in any of this entry and the state is invalid. That's what I need to do. If you have a snoop, you want to see, you want to do a read. So you see, you want read X. You want me to check my PCB to see if I have X in a valid state, so that I can provide you data. Whoops. Any of that. Sorry. any of that, I have to search, but not now. Not during a write. If I have the pointer, when I do a write, I simply follow the pointer, no longer searching. If I have a snoop, I first check the cache line. Okay? If the cache line exists, anything that I need to do, I would need to follow. So suppose it's an invalidation. There's an invalidate external request, invalidate cache line Y. I find it, I say, okay, invalidate Y, and I follow the link to go here, and I set this to superseded state. Okay, again, no search. Okay, so write, I don't need to search. Snoop, I don't need to search if it's a hit. Okay, so all of a sudden, the only time I would need to search the queue becomes just one thing that I miss. Either I'm loading my own cache I miss, or I'm doing a coherence checking and I don't find it in my cache. That's the only time I go and check my PCB. Okay, that's a good thing because miss is far less frequent than hits. Okay, what else can you do? Bloom filter. You've probably heard me talking about this. What's a Bloom filter? It's a probabilistic membership test. Okay? You can imagine it, you can think of it as having as being a hash table. Anything that is that I need to do a membership test. What's a membership test? Why am I searching PCB? I want to see if X is in there. That's a membership test. Okay? Does your PCB have a member called X? Anytime I need to do a membership test, I can use PCB to filter out unwanted or a significant portion of it. So every member in my PCB should have an entry, a hashed entry, for instance, in a hash table. And the bit is set. And when I want to search for a location, I also hash it. And if the bit is unset, then I know I cannot possibly have it. Okay, this is a very commonly used technique to filter out. But the neat trick over here is not just plain Bloom filter. Okay, it's actually the combination between between optimization 1 and optimization 2. Okay, Bloom filter is easy, but if I have 200 entries, then having a gigantic hash table, I have a couple of hundreds of bits, and to make the filter useful, the set bit has to be a minority. Okay, if I have 200 bits in my Bloom filter and I have 300 members, chances are most of my bits are filled with 1. So anytime I hash anything, I find a 1. I'm not filtering anything. I have to still go check the Bloom filter. Okay, so if you have so many members that you need to hash, then you may need to have a very, very large Bloom filter, and that's not good. So what's the observation here? The observation here is if I already have the pointer over here, then I never will need the Bloom filter. I know it's in. I'm following the pointer. Why do I check the Bloom filter? I don't. So the entry Y over here, when it's put into this, it will not have its membership bit set in my Bloom filter. Therefore, the only thing that has a Bloom filter bit set is for an entry who is no longer in the cache line. And this reduces the amount tremendously. Okay? And this reduction helps reduce false positive by more than an order of magnitude, sometimes almost 3 orders of magnitude. Okay? So after these 2 optimizations, here's what happens. I have a whole bunch of benchmarks. On the y-axis, I'm showing you the frequency measured in the number of PCB accesses, meaning an associative search, per 1 million instruction. And these are on the orders of 1 to 4 times 10 to the 50, so hundreds of thousands. right? So every time, so if I don't have any of the optimizations, on average, let's just take a look at the average, and everything else makes sense. On average, in a million instructions, I have about 200,000 checks because of local requests, because I'm doing a load, or because I'm doing a miss, or I'm writing. So out of a million, I'm doing that many PCB accesses. And out of a million, I also have about 50,000 or so search requests from an external agent, a snoop from my neighboring processor to say, I need value X, or I want to invalidate cache line X. Okay, so that's the left-hand side, local request. The right-hand side, remote request. But how many do I really do? It's this color, which if I clean it up, you see, that you cannot even see. It's right here, this sliver. The only time you can see it's right here. Most of them are zero. Not, well, I shouldn't say zero, are effectively negligible. Okay, so what happens? Well, sometimes I'm using filter. So for a lot of local requests, I'm simply using filter. Following the pointer. Other times, it's being filtered out. The yellow color, or this beige color, whatever you want to call this color, is indicated by Bloom filter. Never mind. Don't bother checking. The only time Bloom filter says, yeah, you might have the entry, is this shaded entry. Okay, so on average, it's less than 1% of the access that normally would needed a PCB search now actually does an associative search. 54% of them are filtered out, 45% of them are done using pointer, therefore it's not an associative search. So instead of hundreds of thousands per million instruction, right? Hundreds of thousands per million instruction, the geometric mean is less than 1,000. So this is very useful. PCB can be done, even though it sounds crazy. It can be done, and therefore you can let your L1 serve. So this is the decoupled part of it. Your processor doesn't even know it's in this state. The only thing that it knows is every now and then it's the commit stage is slowed. So your execution speed might be a couple of % slower than otherwise, but it's not doing anything on the timing critical path differently than in a non-redundant execution mode. So there is a problem of this way of doing things. Maybe this is already seen here. What is the problem? The problem is this. My L1 cache, when do I write back to L2? When I have an eviction of a dirty line, that's when I write it back. So in real run, multiple writes to the same location are essentially filtered out by your L1 cache. They all hit in the cache, and when you're all said and done, many cycles later, when the cache line gets evicted, you write it once back to the next level. Well, this is the problem. The problem is this gets exaggerated. This write back gets exaggerated by my PCB. Look at this example over here. In conventional system, when do I write back? Probably just this. Let's pretend this is the last write in a long time. Then this is the only time I'm writing back the cache line. I'm not writing back at the moment. This is the last touch. When the cache line that is touched by this access gets evicted, that's when I'm writing back. So T1 is not writing back, it gets invalidated by T2. T2 is not getting back, it's invalidated by T3. The only time we write back to the next level is at the end of the lifetime of this store. But look what's happening in my design. I have to write it back here because that's the most recent copy. I have to write it back here because that's a newer version, and I will write it back here again. So I wrote back 3 times instead of once. That's what gets the bandwidth consumption up. Is it a big problem? Should we worry about it? Turns out it wasn't a big problem to start with. Here's a view of this. Again, we'll just look at the average. There are 3 bars that I'm showing from left to right. They're non-redundant execution, redundant execution because of BCB, and some optimized version. Okay, so if you compare this guy over here, that's the amount of traffic you get if you run the program. You know, in our case, 16-core processor, I'm running 8 threads. This is the amount of traffic, and it's a certain percentage of the total bandwidth available. And it's further broken down into the read request from the compute and write back. Okay, now let's look at what happens when I double up, when I use all 16 processor to run the redundant version. Now, of course, my bandwidth would double. I expect that, right? Instead of 1x resource, when I'm executing redundantly, I need 2x the resources. I need 2x the processors, and just by association, perhaps 2x of the bandwidth, but it's more than 2x. Okay, so the verification thread actually reads a little bit less than the compute wavefront. This is a small technicality because we pass on branch prediction results, so there's very little wrong path execution. But it doesn't matter in the grand scheme of things. This part is the same. So you see the read part, the brown color and the blue color is about the same. But this is how much write back happens now. It's a couple of times that of the original. But thankfully, it wasn't too bad. Okay, it was about 30% of all your traffic. Okay, so it's not terrible. You can tolerate that. But if you don't like it, there's some optimization you can do. And the insight was this, that, oh, wait a minute, I don't need to write this back. If I realize I'm already finished validating this epoch, so this version is the one that I can write back rather than this one. So I can skip this write back. So if I have more epoch, this is what I do. I keep the value around longer, and anytime I figured out I have something that's already superseding an earlier version, and I can go in, take that out, so when this thing gets recycled, we don't have to write back as much. And if you do that, if I can clear this, if you do that, you kind of reduce, well, almost half from maybe using a different color because it's quite reddish. Instead of this block that you have, right? Instead of this much, right? By doing this delayed and therefore efficient write-up, I cut that by about half, and now my overhead is much smaller than before, so maybe I doubled it. But you just measure, let's measure the total, right? This is what you would expect. This is what you run when you have 8 processor, and this is what you have when you have 16 processors. So it's about 2x, a little bit more, not too much. So this can be done. That's the message. There is not a whole lot of problem that makes this exceedingly expensive and all that. So the one last thing about all this is non-determinism. Okay, if I run it every now and then, I get some non-deterministic execution-induced difference in opinion. What do? I cannot just roll back and re-execute, because next time we may still differ in the outcome. So you have to suppress that. Remember, this is due to a race. You have to suppress race. Whatever race is played out in the compute wavefront, it has to be played out the same way in the verification wavefront. So you have to slow down some instructions simply just by putting pipeline bubbles, if you wish, to delay it. Okay. So how do you do that? Well, you record the timing. You record meticulously at what cycle which instruction got there. So some way of telling the trailing wavefront. So the trailing wavefront may simply say, okay, this instruction was executed in cycle 24. So right now it's cycle 20. Let's not issue this instruction and wait until it's cycle 24. You can do that, okay? But you don't want to record too much timing, right? And a lot of the timings don't really matter. Remember, a race has to involve two memory accesses to the same location. If they are not to the same location, who cares? They can get out of order, and you will not suffer a race-induced non-deterministic outcome. And how do you know there's a race? Well, look at this. You tell me what is the one concept that you already know that is related to this event. Two memory accesses in two different processors to the same location. One of them is a store. A coherence request. It's either an intervention, if it's the read is after the write, or invalidation when the write is after the read from another processor. So you know when this happens. The underlying cache coherence or shared memory substrate will let you know. Okay? Then you can remember only those events. Oh, I had an invalidation and it was from processor 3. That means whatever load that I had committed up to this point was before that store that triggered this new invalidation. Okay? And in fact, you don't have to remember even that. What we propose to do is the following. We have the notion of a sub-epoch. Okay? So the epoch is a long time. Within an epoch, we want to coarsely organize the number of instructions. Maybe the first 35 belongs to sub-epoch 1, the next 35 or 200 sub-epoch 2. That's what we want to do, because then how do we record order? We simply pass on this vector that says the first sub-epoch has this many instructions, the next has that many instructions. We pass this on to the verification wavefront. And the verification wavefront would therefore, basically essentially do a barrier. Every time you're done with the first sub-epoch, you raise a barrier and you stop your own commit stage. And when everybody finished committing their first sub-epoch instruction, you can then start to retire the next sub-epoch. So this is what we do. Whenever there is an invalidation, so let's say this store that we have, it triggered an invalidation, okay? And that means we have a potential race, okay? We don't know if it is a real race. I mean, it is a race, but we don't know if it's a guaranteed race that's not subsumed by another race. Never mind. So we know that this can potentially be a race. We don't know if the race is so far apart that it's practically not possible to get a different outcome. For instance, at the moment, I had to issue this instruction. It had to invalidate this guy, and we detected this. We say, oh, you know what? Some load instruction in this thread executed before my store, but that load instruction might be belonging to a much earlier epoch, so there's no way we can get out of order. Okay? But as long as there's a potential race, what we do is we tell everybody, we broadcast. At the moment we detect such an event, we tell everybody to say, okay, just keep a count of how many instructions you already committed, and that's your sub epoch I. Okay, everybody who gets this request simply marks this, and this is your sub epoch boundary. Okay, and what happens is every time in an epoch, at the end of the epoch, you pass on, remember, your checkpoint state. You also pass on the number of instructions in each sub epoch, and then you can basically use this to control non-determinism. Okay, so how do I know I have such an event to trigger? Well, you already have the hardware. It's a tag, it's data. Okay, that's your cache. Now we're adding 2 little bits to make this work. One bit is a read, the other is a write. Okay, when you have an access that read a location, you go and mark it. So if you have a load, you mark it. When you have a store, you mark that. And then when you have an external invalidation or coherence message, let's say in this case it's about X, I take a look. I see that I read from it at some point. Now I'm going to say, okay, this is one of those potential race conditions. What do? Boom, we tell everybody to create this boundary, and at the same time I'm clearing that to 0. So now in the new epoch, what happens? So if I received an invalidation request, let's say to Y, I would check and see, no, I didn't do anything, so this is unrelated to me. I will not issue this let's increment our epoch command. Now, once we did that, do we really have to rigorously following the original order? And it turns out it's not necessary. You can always make sure that whatever is the epoch situation in the compute wavefront, the verification wavefront does exactly the same thing. You can do that, okay? But that can be a little bit too slow. Okay? And this is somewhat shown in here. Again, if we just look at the average, I can run 8 versions, and this is the normal execution. And if I have the strict enforcement, if I have a run where I run the loop, the compute wavefront, verification wavefront, the verification wavefront is run in a certain way so that it never ever has a non-deterministic outcome. It's a bit slow, as in here. This is what we call strict enforcement. In fact, you can do selective enforcement or even blind speculation. What's blind speculation? Blind speculation says this: who says I will have a race? Yes, I have all these sub-epoch boundaries. Why can't I optimistically assume we will never have any non-deterministic outcome, and just commit whatever we want? But if you have a problem, if at the end of the epoch you compare, you say, whoa, the result is not the same, the very first suspicion has to be, okay, you know what, it's because we have a race. Then you have to roll back to the beginning of the epoch, this time enforce the sub-epoch boundary. Then you rule out the situation that is race-based. If you still have an error, obviously it's a soft error, or hard error, it's a hardware error. So if you do that, it's quite a bit faster. We even had a small optimization. It didn't turn out to work that well. The select enforcement says, let's be a little bit smart. In an epoch that we think we have this problem, we're going to do it. If we don't think there is a problem, we're just going to speculate up front. it doesn't work very well. So blind speculation works out pretty well. So the point is really that the non-determinism can be surprised using pretty cheap approach. So it's not difficult. The hardware that we have is off the critical path. The activity only affects or mainly affects cache misses, and your core doesn't even know that we're in redundant execution for most of the time. And we did manage to protect memory logic. None of this says let's pass on the value from the computing wavefront to the trailing wavefront. We allow them to independently access their memory. Yes, there's going to be possible non-determinism, but that can be controlled fairly straightforward in a fairly straightforward manner. Okay, you don't need to pass on values, which is very bad because any error that happens in the memory dependence logic coherent substrate is not being checked out. The overhead is pretty tolerable. The performance loss is less than 3%. Okay, meaning if you run, well, you lose throughput. Okay, to run a redundant version of a thread, you need 16 processors. So you do lose that. There is no going around that. But if you do have the throughput, your execution speed is only impacted by about 3%, less than 3%. And the storage overhead is rather small at about 11 kilobytes. So this is the way to do it. And again, I mentioned this early, if you have a processor that runs very buggy OS, the chance of a particle induced or any environmental noise driven hardware error, in our experience, based on what we hear, based on what is reported by other researchers, is not your main concern. So you may have a thread level redundant design for the purpose of marketing, to tell people, oh, our system is more reliable because it has this. Yes, it is in theory more reliable, but in practice, it's not the main, you're not addressing the main problem of your system's reliability if your software is buggy. So, but if you do have a situation where you want reliability, I think there is a right way of doing it that doesn't involve some of the unnecessary trade-offs that we mentioned. So that concludes this part. Next time we'll move on to a different topic.